All right, hi everybody. Thank you for the introduction. Savvy is such a strong word. I dabbled in quite a few languages though. As soon as I'm up here, there we go. We'll come to that. So today I want to talk a bit about distributed tracing and error monitoring. This is what we do at Sentry. The talk is, however, not going to be focused on our product. But distributed tracing is done all over the industry. There's some just general things that hold true for all vendors. First off, a quick intro to what Sentry is. Anybody here already have experience with Sentry? Know it? Okay, cool. Quite a few. So we are a application monitoring solution. We actually come from a background of monitoring errors, which is still like our strong suit and what the company is has been built on. And now we also do like monitoring in terms of performance, and as I said, that distributed tracing thing to give our users or you, the developers, insights to where an application is slow and where we can improve stuff and give you as much context as possible to fix that. So we kind of see a slow user experience as a form of error, if you will. Then a quick intro of myself. I've been in the software industry for the last 12 years, did app development and a bit of backend development in a small company where I got to play around with quite a few of languages, Kotlin, Swift. Also had the pleasure of working with Objective-C, if anybody remembers that. And then 2 years ago, I joined Sentry as a contractor and have since been working on the Java SDK. So what am I going to talk about? Intro is done. Quick history of why we would need distributed tracing and not just use good old logs. Then how distributed tracing works, how we match that with error monitoring, and then I'll try to give you a quick live demo. Fingers crossed that works. And then a few closing words. All right, so how did we get here? Well, how it started, we had a trusted old web server, maybe that was an Apache one, and each request from a browser would sort of spawn a sub-process which would have their own logs, and the browsers were much simpler than as well, so they basically gave us a request and returned them HTML. They displayed that, all good. If we had to figure out an error, well, we could basically trace the whole request in that one log file of that subprocess. So logging was a good solution for that. Things changed quite a bit since then. We got concurrency models, so our browser request wouldn't only go through one subprocess and then into the logs, but maybe it would spawn a thread, which would spawn another thread, and it would intercommunicate and so on. And then we needed to find a way to make that log readable. So maybe we attached some sort of unique identifier to that request. For that, well, concurrency was quite manageable because we could trace that request again through the log we had. Now, through the advent of Docker, Kubernetes, Cloud Functions, and so on, things got a wee bit more complicated. So we don't have just multiple threads on a single server, we have multiple threads on different, for example, Docker containers on the same server, or on a serverless environment, or on distributed servers all over the world. So we actually collect a multitude of logs in different locations. Now figuring out what was going wrong in that single request sort of starts to have some similarities to finding a needle in the haystack. So again, we need to find something that can help us with that. And this is, oh, sorry, changed on my screen before yours, sorry. And this is where distributed tracing comes in. So, a few words on distributed tracing. We start off with a system. Let's say that's our front end. And the sort of minimal or the smallest unit of work that we can trace is called a span. The first span here, this is called the root span. And when we create that root span, we would also start the trace. And the trace is basically a thing that would run from user action to completion of that whole chain of requests that go through a multitude of systems. To that root span, or any span, we can attach some metadata that we can then use to give more context to whoever is then trying to infer something about what happened in that trace. We have a start and an end of a span, so we can measure how long specific things took. And spans can start other spans and have spans that are nested and so on. So, as I said, the span starts by a user, for example, opening our front end, be it a mobile app or a web application, and wants to do something. I don't know, log in, for example. And each method that we want to, or that we instrument. So of course, each library, doesn't matter which vendor you use, they somehow need to know what you want to track. So we instrument a certain method, for example, and that would start a span, and also end it once the method is done. Each span gets a unique span ID, and each trace, of course, has its own ID as well. The root span here is the only one without a parent. All the other ones are basically created from that root span. So then at some point, the user clicked our login. Maybe we did some work on the front end before that to have some other spans in there. And at some point, we need to cross system boundaries. So from the browser to a backend. This is where we send a network request, and we add in a header with the trace ID and a span ID, and actually a third value, which is just a 0 or a 1, which means, well, did that front end decide to track that span or not? I'll come to that in a minute. And with these values, actually, our next server or service can continue that trace with that information. So this span here, whoops, where's my mouse? Span here would have that span as its parent, and it would know to continue exactly this trace. And then each system would send all that information to some sort of data collector, because we need some system where we can actually extract that information again and look at it. In our particular example, that would be Sentry, because for obvious reasons, I do work for them and I'm not going to use another one. But there's a multitude out there. And then in that system, this whole information gets processed, spans are being linked together, and then displayed in some sort of flame chart, for example. Also, this could happen that somewhere along that chain of spans, an error occurs. And then we need to somehow match that error together with our trace data, and then be able to display that information to the user. So with all of that, we can actually extract some key benefits. So we can pinpoint performance issues, because everything that is given a fully instrumented system. Stuff that we don't instrument, we can't figure out if it's taking longer or not. But we can pinpoint performance issues, figure out what is going slow, and then focus our optimization in that area. We can investigate exceptions. So with that logging, we can sort of match those exceptions to a certain span, and then hopefully have enough information by having like the whole trace that leads up to that exception to give us enough context to figure out where that originated from. and what the problem was that caused that exception. It should save us quite some time by not sifting through a multitude of logs on a multitude of systems, hopefully, and should also give us insights on how our data flows through our different systems. Of course, it's not all sunshine, so we do have some drawbacks that we need to consider. One of this is sampling. It's not really feasible to have a huge system with, I don't know, maybe 100 microservices, send each trace for each request to another system, which then would need to be even bigger to be able to handle all that load. And that's why we need to sample stuff. So we have like a percentage of requests that we want to sample, and these are then going to be sent to our data collection system. So the gist is finding the right balance between sampling enough, so we get enough information, and not sampling too much, not to overload, for example, that external system or our own, because we do need to make additional requests to another external system. And another problem that we need to take care of is time skew. All our measurements might look weird or screwed up in later on in the visualization if the times of the servers don't match. For servers, there's a pretty good fix called the network time protocol, but we can't guarantee that on clients. Mobile devices shouldn't be that big of a problem because they usually just sync their time with the network provider. Browsers and users' personal computers are a bit of a different story, but this is something that we need to live with because we can't force that on them. And then here's a very simple example of how we at Sentry correlate those spans with errors. So we can also show some Kotlin code. So if we want to instrument that process item function, we would first check if we've got an active span, and if not, we would start a transaction. A transaction is something that is specific to Sentry, which is nothing more than a container for all the spans within the given system. So all the spans within the front end would make up the transaction. And then if there's exception there, we catch it and we attach that throwable to our span. And that information then also gets sent to our backends, and in there we match the exceptions together with that particular span. In the background it's a bit more complicated, but this is everything that a user needs to know. All right, so this is the basic idea of it. And with that, I'll try to hop into a live demo. And a quick note on the live demo setup. And show. So I've set up 2 Spring Boot backends with controllers there. They are very, very simple, and for somehow the highlighting doesn't work here. But anyway, we've got one system that basically holds a database with a list of user nodes, and a second system that sort of takes care of getting the user ID. This could be our authentication service, for example. And a small Android app, which doesn't do anything other than show a list of those nodes. So if we're going to add a new node here, that takes a long time. And we go over here. We should see the second one. Now that whole request took quite a bit of time. Let's see if we can find out what the issue was here. Of course, I don't have any transactions. In that case, I'll look into the backend directly. Okay, so we got the first one, the nodes add. That took quite a long time as well, so we can drill into that. And in there, it tells us, well, that took over 2 seconds just to save something in a in-memory database. And then we can drill into that further, and this is a flame graph. We can actually drill into it and see, well, this one authenticate method here took up basically all the time of that request. So this is the trace in the backend. We got, this is where we started it. Then we got a call to add nodes, and then we did another call to the next service, and in there we had that authenticate method, which took up all the time. With that information, we should be able to actually sort of figure out what went wrong, which in our case is rather easy, because somebody forgot to delete test code. Let's delete that and rerun that one. Oh, perfect. There we go. And with that one, we should be able to see another recent transactions. So this one was quite a bit faster, and we see our performance problem here is basically gone. So this takes only very little time, and then we see this is how it's supposed to be. The HTTP request is basically the most complicated thing that we do in that sample. So this is also where all the time is going. Another thing that could happen is, of course, that we somewhere run into an error, and we should be able to figure out that as well. Either through transactions, or let's go into the issues part. We see our call to adding nodes, encountered an error, and from there we can see where that error originated. And if we want to see how that thing basically flowed through the tracing, we can again open up that view, and we see, oh, okay. Again, that second system that's supposed to authenticate our user is the culprit here, and in there we have the exception that's being thrown. Which again comes down to some testing code, which we can just fix up, and then we're again good to go. So unfortunately, the performance stuff with the Android app didn't work out, because otherwise we'd have seen a bit more, or a deeper sort of flame graph with all the timings that we take from the Android app as well. But yeah, this is basically how such a trace view looks like, and how that could help us to pinpoint issues within our code. With that, I'm back to the presentation. So, as a quick update at the end, a few notes on the Java SDK as well. Why did we choose Java? It's called Java SDK, but this is also what we use for instrumenting Kotlin code. But the decision to stick with Java for the base SDK is because there's people out there that still develop in Java only, and we don't want to make their apps bigger than they need to be by attaching the whole Kotlin standard library, for example. Our specialized Android editions are written in Kotlin, though. For example, we have a thing for Kotlin coroutines, which needs to be in Kotlin. And what's next? We are in the midst of fully integrating OpenTelemetry into the Sentry SDK. Anybody have heard already about OpenTelemetry? Oh, quite a few, okay. So this is basically the de facto standard for auto-instrumenting code. And with that, we actually get quite a few of new integrations that we can use and leverage. This is actually something we're planning to release an alpha version in the next 2 or 3 weeks. Let's see how the testing goes. All right, so as I've heard, there's a few people already knowing Sentry here at ING. A few teams already using it. And if you're interested in having a talk with them, here are a few names of the guys that are sort of spearheading using Sentry at ING. And of course, you can also always visit us just on Sentry.io, or if you want to sift through some code, Sentry is developed in the open, so just head over to GitHub /GetSentry, and you can actually look up everything I just said, and hopefully didn't make too many mistakes. All right, okay, that's it from my side. Thank you very much.
If you want, Lukas, we have like 2 minutes for questions. If there are any in the room, there is a question.
Oh, yeah.
Thanks. 1, 2, 1, 2. Yeah, thanks. So there was one Kotlin snippet. So they released recently auto-closable. So maybe as a feature request, you can implement auto-closable, then that code will be nicer.
Yeah, we actually, because I just said we're implementing OpenTelemetry. They're using auto-closable in their SDK quite heavily as well. And because of that, we are starting to migrate to that too in quite a few things, especially in starting transactions and starting spans. Okay, if there's no more questions, then
I don't
thank you.
think so. No, thank you very much.